طيب بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so this is a new lecture and today we are going to talk about object detection algorithm. So in the previous lecture we have talked about the different classification algorithms, the state-of-the-art algorithms that were proposed since the AlexNet in 2012. Okay, and we have presented the architecture of different ones and their evolution starting from AlexNet and ResNet, GoogleNet, VGGNet, and Inception as well, and the different characteristics of all of them. And as you remember, so AlexNet is the first one that have actually triggered the use of deep neural network for computer vision applications. And then after this, there is a huge efforts that was done and a lot of achievement for developing classification algorithms. And now we have a good bunch of algorithms that perform classification. And in this plot here, you can see the performance of these for providing top 1 accuracy. And also, this is a scatter plot that shows the performance in terms of the number of operations and the top 1 accuracy. So there is always a trade-off to do in what concerns classification algorithms in terms of performance and accuracy as well. So in today's lecture, we'll talk about detection algorithms or object detection algorithms. And the learning outcomes will be to understand the difference between object classification, object localization, and object detection, also landmark finding. You will also understand and implement the concept of non-max suppression. We will also introduce the intersection over union metric, and you will understand how we label a data set for an object detection application. So what is object localization? So far what we have done so far is actually object classification. We have an input image. Okay, it contains one main object, for example, a cat, and then we're going to process this image through a convolutional neural network or a neural network, and finally it's going to tell us what is the main object in the image. This is what we call image classification. And today we are going to learn about classification and localization. So what does it mean? We will not only say that there is a cat inside the image, but also we will identify the location of the cat in the image. And the identification of the location of the cat in the image will be done through what we call a rectangle or a bounding box like this. So you will learn how to characterize a bounding box into an image and to localize an object into an image. So classification plus localization is the case when you have only one object to localize, like in this case. But a more general concept is to localize multiple objects. Okay, so in this case, we move to another concept that is called object detection. So object detection is like detecting and localizing multiple instances into the image. So providing an image like this, we can say that there is a dog, it's located in this location here, there is another cat here, there is another cat here, there is a duck here. So it's possible to find all the different classes and also to provide the location of the different classes. Okay, so first we are going to learn how to do localization. Okay, and then we are going to generalize the concept of localization for object detection. Also, we have the instance segmentation. Okay, so instance segmentation here, we're not going to provide bounding boxes, but we are going to provide we will make the labeling of the pixel. Okay, all the pixels representing a cat and all the pixels representing a dog and so on. So this is actually pixel-wise labeling. And here we just label like the whole bounding box of the image. So this is the difference between object detection and segmentation as well. But in this lecture, we are going to introduce classification and localization and object detection. Okay, so this is just another slide about the three different types of classification with localization, and object detection problem. And this here you can find some more detailed definitions if you want. So to summarize, image classification just classify a picture, and here we are going to predict only a probability of an object. What is the probability that this object is, for example, a teddy bear? And in the second class is classification and localization. We detect an object in the picture and we predict the probability in the object and also where it is located. And also here, and in the detection, we are going to detect all the different objects and where they are located. Okay, so let's review now the concept of object classification. How did we do object classification? So usually we have an input image like this. Okay, it's an RGB image. So it's split into green, blue, and red channels, into 3 channels, and it has certain dimensions, for example, 600 by 400. And then it will be processed through a convolutional network. So here we have some filters they are going to process, and it will go through several layers. And finally, it will output a convolution or a feature map. And this feature map is going to go through a fully connected network. And the output layer will be a softmax function. So what the softmax function will have as output, it will just provide you the probability of the object that will be located in the image. For example, if we provide an image like this, so it may return, for example, this is a cat with probability 98%, this is a dog with probability only 1%, and a bird with probability 1%. So what we will do, we are going to take the instance or the object with the maximum probability. This is the case of object classification. Okay, so this is the algorithm. You have an input image, you have several layers of convolutions, max pooling, and nonlinear ReLU functions. You do these operations several times, and finally you have fully connected layer, and the softmax function will output numbers between 0 and 1, giving the probability of the images. Now, this is the difference with between object classification and object classification with localization. So now we have an image like this, and we're going to classify this image as there is a cat in this image, but we would like to know additional information. Is that where is the location of this cat exactly? So now the first question we need to answer is how to represent an object. Okay, so we are going to represent an object using a bounding box, which is just a rectangle that will go very close to the object like this. And the bounding box or a rectangle is specified by some parameters. It's specified by a center point and the width. Okay, the width and the height. So this is the bounding box here, and it has a center point, and then it has a width, and it has a height. If I have the information about the center point, the width, and the height, in this case, I can specify the location of the object detected in the image. Okay, so now the convention of representing the center point, the width, and the height, we're going to consider this is the point 0, 0 in the image, and the point here will be considered as 1, 1. And all the values here will be between 0 and 1. It represents like proportion, okay, along the x-axis and the y-axis. And now you have to specify, for example, what is the coordinate of this center point of the bounding box inside the image. Okay, it will be a value between 0 and 1. For example, here bx. So if we consider this is the x-axis and this is here the y-axis, bx is equal, for example, to 0.6, and by, okay, along the y-axis will be, it's almost around 0.5. Okay, so this is now the coordinate of the center point. And then we need to specify the width of the bounding box, bw, the proportion of the bounding box with respect to the overall image width. So for example, looking at this width here, it's almost half of the total image width. So here we will say that the width of the bounding box will be 0.5. What does it mean 0.5? It means half of the total image width. And the same thing will be also for the height of the bounding box, will be expressed as percentage. So you can see here, it's almost 90% of the total height of the image. So that's why we can put it equal to 0.9. Okay, so now, having understood this, so this is now our expected output if we are going to perform object classification and localization. So the output is not going to be only a probability 0 or 1 regarding the class of the object, but also it will output the coordinate of the bounding box, its width, and its height. Okay? And now, if we look at our output here, it will contain these four information, bx, by, bw, and bh, which are the coordinate of the bounding box. And it will contain a probability whether the object exists or not. Okay, so if it is equal to 1, it means that there is an object that is detected in the image. And if it is 0, it means that there is no object detected in the image. And here it will, then if we detect, if the probability is 1 here, then we will tell what is the object that is detected. Is it a cat or a dog or a bird? Let's assume that we have only 3 classes here, cat and dog and a bird. So for example, if we input this image here, it will say that there is an object detected. These are the coordinate of the bounding box and the width and the height. And now the probability that it is a cat, it's equal to 1. The probability that it is a dog, it's equal to 0. And the probability that it is a bird is equal to 0. Okay? And this is now the expected output for object classification and localization. And again, we are going to use a convolutional neural network that will output this information over here after multiple convolution and nonlinear layers. So we will do the same principle. What is going to change is the output. So here the output was only a softmax function providing 3 probabilities, but we are going to add to these 3 probabilities the bounding box, coordinate, width, and height, and also whether there is an object detected or there is no object detected. Is it clear until now? Okay. So this information will, just to finish, this information will be encoded here, bx, by, bw, and bh. The probability that there is an object Okay, if it is 1, it means that there is an object, and then we are going to look which object through the 3 probabilities here. And if it is 0, all these parameters will be just ignored because there is no object. Yes, what's the question? No, you mean during the labeling? Yes, during the labeling you do the bounding box yourself. But later on, now this is in the training. In the training, it is going to learn how to output the bounding box coordinates. So this is why we do the labeling. And now every input image, so when we input an image for an object classifier and localizer, it's going to take the image, the class, and also the bounding box. So it's going to learn how to make bounding boxes for unseen images in the test data set. So it will not only learn the class, but it will also learn how to make a bounding box. Yes, it will give different result and it will give a different accuracy. That is why when we do the labeling, and you have been doing the labeling so many times, we always want that the bounding box is very close to the object. Okay, so we try to minimize the background and the noise that is in the background with respect to the object. So of course, so if you make very large bounding boxes, this is going to affect the training later on. Okay, and it will have an impact on the performance, obviously. Okay, so let's look at this example now. If we want to apply this concept on different images, for example, if now I provide an image like this. So here, the output will be 1 because there is an object. So let's assume that we have object cat and dog and bird. So here there is an object, so the probability is going to be 1. So 08, 07 will be the center of the bounding box, and 05 and 05 will be the width and the height of the bounding box. And then here, probability that it is a cat is equal to 1, and the probability that it is a dog 0, and the probability that it is a dog is 0. So same thing now, if we apply another image like this, it will return 1. Okay, let's assume it's going to give some values for the bounding box, center, the width and the height, and then the probability that it is a cat will be 0, the probability that it is a dog is equal to 1, and the probability that it is a bird is equal to 0. Now, if you put an image like this where there is no object, okay, well, there is a tree, but the tree here doesn't make part of our 3 classes. So for the classifier, there is no object. So in this case, it's going just to input 0 here, to output 0 here, and all these values, they will be ignored because there is no object. Okay, so this is actually the way on how we perform classification and localization. So what changed is actually the format of the output, because the output will contain more information, not only the classes, but also the information about the bounding boxes and the information about whether an object is present or not present in the image. Okay, so to summarize, the detection in the context of object detection, different methods are used depending on whether we just want to locate the object or detect a more complex shape of the image. Okay, so I have presented the bounding box detection now, but also there is another thing that is called landmark detection. And this is something that we are going to do later on when we talk about face recognition and some other deep learning applications. So in some deep learning applications, we don't need actually to pass the whole image into a convolutional network for detection, but try first to identify some features, okay, that are point of interest or landmarks. We detect a shape or a characteristic of an object. For example, we can put the landmark like the eyes or here the different joints of the body and so on. Even in this is what we call also embedding for face recognition. We try to extract some reference points from an image, and these reference points will be later on used for the detection or for the classification. Okay, so we will talk about landmark detection with more detail later. Yes. Sorry. Yes. Yes, it's basically used for face recognition because now face recognition is more complex. Okay, it's really difficult to now for face recognition. It's not easy to take multiple images of multiple persons to make the training. So we would actually like to make the detection from only one person face. Okay, so this is why the technique is different. So what they will do, they will extract some important features from the face, like a vector of dimension 128 values, and these 128 values will represent the feature vectors or the landmarks that will be used for making the detection using some machine learning algorithms. Okay, so it's a way to reduce the dimensionality. Instead of inputting the whole image, which is large in size, we will extract just point of interest, and then we will use techniques in order to make pattern matching. Voila. Okay, so now we have talked about object classification. And the next is about object detection. So what is the difference between object detection and object classification and localization? So simply here, we're going to detect multiple objects, okay, multiple objects. And the overall idea here is that we are going to take several windows of the image, and every window we're going to apply a convolutional neural network. Okay, so for example, I will take this window here and then pass it through a classifier, and then the classifier will tell me whether there is an object. It will apply just the object localization, classification and localization. But we will not do the whole image as a whole, because here the images will be containing a lot of images or a lot of objects. So we take this part here and this part here, this part here, this part here, and every sub-image is going to be processed by an object detector or classifier. So this is the algorithm. First of all, make a window of a size much smaller than the actual image size. So then we crop the image according to that window, and we pass this cropped image into a convolutional neural network and have the ConvNet make the prediction, like we did for the object classification and localization. And then slide the window and pass the cropped images one by one to the ConvNet. Okay, I will show you now the process in a while. And after cropping all the portions of the images with this window, repeat all the steps again for a bit bigger window size. We will do another window size, because maybe this window size is very small or it's very big. So we will try different sizes of windows. And every time we do predictions. At the end, you will have all cropped regions which have some object together with the class and bounding boxes of the object. Okay, so this is the process. Imagine that you have an image like this. Okay, so in this image, we can clearly see that there are two cars. Okay, so what we will do, let's take a first bounding box like this. Not a bounding box, let's say a first window. We call this window. And then we will take this window. Okay, let's start by the top left side of the image. So here we will pass it through a ConvNet. There is no object, so we go to the next window. And here we will do the same thing. There is no object. And you keep doing the same thing. Okay, this is what we call the sliding window concept. Okay, going through all the parts of the image one by one, one by one, one by one. Okay, until hopefully it can find an object or part of the object. Maybe if you pass this through a classifier, it will tell that there is a car, depending on how you have trained your network. Or maybe if you pass this, it can also tell that there is a car, and so on. So this is the idea of the sliding window. Okay. Yes. Yeah, it's hyperparameter. It's like they have the strides. When we do convolution, you have the stride. Okay. Okay, so now it's like the stride. Okay, you can jump with how many pixels you want. It's hyperparameter as well. So now we can do the same thing also with the bigger window size. You can do using a bigger window size like this. Okay, and then you repeat the process. Maybe you will be more lucky to find some other object in this window size that is a little bit bigger. Okay, and you keep doing the same thing. So you can do this for a certain number of window sizes depending on the size of your original image and the size of your object that you have. But this is actually the concept. And then you can do also with another size similar to this one. Okay, and you can see every time you will apply this algorithm with the hope to find several objects. Okay, so this is the concept of the sliding window. But of course here, there can be a drawback, because now we are going to fix a sliding window with a certain size, let's say a square like this. And you may predict, for example, your predicted box is this one, but actually the real car box or bounding box is this green one. So it's not going to be very accurate later on in the prediction. It's true that it's going to tell you that there is a car here, but the bounding box, the predicted bounding box is not going to be as accurate as the original or the actual bounding box. This is one of the drawbacks of the sliding window. Added to this also, it is very slow. Okay, because when we have images, and if you do this process several times on the same image, it's going to take very long time. And this is not, it's intuitive approach, but it is not very efficient in terms of computation efficiency. So here we provide the summary of the sliding window approach. This solution is known as object detection with a sliding window. It is very basic solution which has many caveats as the following. First of all, it is computationally expensive, because cropping multiple images and passing them through a ConvNet is going to be computationally very expensive. That's true. And the solution here, that instead of making sliding window and cropping the images, we are going to replace this computation intensive operation with a convolution. So I will show you how we can implement the sliding window using a convolution one by one. Okay, one by one convolution layers. It will replace all this sliding window technique. Okay, which will be more efficient. And this is actually the concept introduced by YOLO. So by the end of this lecture, you will understand how YOLO is actually implemented. And YOLO is considered as the fastest object detection algorithm so far, and probably now EfficientNet is taking over in terms of efficiency and also accuracy. But YOLO, for the last 3 or 4 years, it has been #1, at least for the performance in terms of real-time performance of YOLO. And you will see why. Because it will replace the sliding window approach that is very time-consuming with just convolutions. And in this case, you don't need to pass the image several times with several windows into the neural network, but you will pass the image only one time. And it is called YOLO. You look only once. Okay, you look only once. It means you pass the image only once into the ConvNet to find all the object inside. And you will see how this is done. And the second drawback, as already introduced in the previous slide, is that it results in inaccurate bounding boxes. Okay, we are sliding windows of square shape over all the images, and maybe the object, they don't have the square shape. They have a rectangular shape or some different other shapes. So in this case, there will be some kind of inaccuracy later on in the prediction. So we will see how to solve these two problems. So these problems were addressed by YOLO algorithm, the object detection algorithm. So the first problem, that is about the sliding window computationally expensive operation, it was replaced by one-by-one convolution. So what is the concept of one-by-one convolution? The idea here is to turn the fully connected layers into convolutional layers. So let's first of all understand how to do this, and then we will generalize this into the object detection context to see how we can use convolution for object detection. So let's take a very simple example, an input image of 14 by 14 by 3. Okay, and then you will apply convolution with a filter 5 by 5. It will result in an output volume like this, feature map 10 by 10 by 16, and then you have max pooling 5 by 5 by 16, and then you have a fully connected layer, another fully connected layer, and finally a softmax layer with 4 outputs. This is like the traditional convolution neural network for object classification and so on. And now we will do the same thing, okay, until the max pooling here. But now we are going to replace the fully connected layer with a convolution. So here, if you look, how many values we have in this first fully connected layer? We have 400. 400, yes. So instead of making a fully connected layer, what we can do, we can make another convolution, okay, that is 5 by 5, 400 times. Okay, so if you apply a 5 by 5 filters 400 times, is going to result into 1 by 1 multiplied by 400. So how many values we will have here? We will have 400 as well. Instead of having just a vector like this, you will have a volume that is 1 by 1 by 400. So mathematically, this is the same thing. It will give almost the same result here. Okay, but this now, this volume is obtained by applying a convolutional operation with 5 by 5 filter, okay, 400 times over this feature map here. Okay, so if you apply 5 by 5 by 16, you're going to find 1 by 1, and if you apply this 400 times, you will have a volume 1 by 1 by 400. And you will do the same thing. You will do a convolution 1 by 1, 400 times, and you will have another volume of 1 by 1 by 400. And finally, you can have a volume 1 by 1 by 4. So this is just, this model is equivalent to this one. So here we use a fully connected layer, and here we change the fully connected layer into convolutional layer. But at the end, we will have the same number of values into this layer, or this layer, or this layer, or this layer here. Okay, so now this is the concept of how to turn the fully connected layer into convolution layer. Now the next question, why we need to do this? How this is going to be helpful for us for the case of the object detection? And this is what I'm going to explain in the next slide. So far, is there any question for this slide? Is this understood? Okay, so now this, yes? Yes. Yeah. Yeah, it's here we have 400 filters and 5 by 5 dimension. So if you make the formula that we learned in the first lecture of convolutional network, you will find the output will be 1 by 1 by 400. Okay, so same thing here and same thing here. And here you're going to make a filter of only 4 here. Okay, so this is just to know that it's possible to turn a fully connected layer into a convolution layer. Now the question, why we have to do this? How this is important for us in the context of object detection? And let's look at this. Now imagine that you have 14 by 14 by 3, same thing. So this is actually the same process that we have done in the previous slide. But here, instead of making the 3-dimension, I just show the front of the volume. Okay, but this is actually a volume, this is a volume, this is a volume, and so on. These are different volumes, but just show the first one like this. Now imagine that you have an image like this, 16 by 16 by 3. And you will do the same thing. So now if we input this part of the image, if we crop this part of the image, okay, we can actually make a convolutional neural network like this. So it will result in what? It will result at the end an output 1 by 1 by 4. صح ولا? If I just input this part of the image, it's the same as this one. صح ولا? It will result in an output 1 by 1 by 4. And now, if I crop the image from this side, and I will take, it will be 14 by 14 by 3, this green part. So if I apply it into a convolutional neural network, it will also generate another 1 by 1 by 4. And here, if I take this cropped part of the image, it's 14 by 14 by 3 as well. It will also generate 1 by 1 by 4 output at the end. And here, it will generate the same output. So what we will say, so every square here is going to generate a softmax output 1 by 1 by 4. Okay, so if we apply this in the same way, what we will generate 4 volumes. Every one is 1 by 4. So here it will be in total 2 by 2 by 4 output. So this one will correspond to this red part, red square here, and the second will correspond to the green, then to the orange square, and then to the blue square. Okay, and now every cropped image is going to return for me a softmax function telling whether there is an object or there is no object. Okay, so here it's like of aggregating the output of all the cropped images into a single output. واضحة الفكرة ولا لا؟ Okay, no problem. So now in the previous slide we said that it's possible now we have understood that it's possible to remove the fully connected layer and replace them by a convolutional layer. Okay, and so this is what we have. Now what is the rule? Now imagine that you have 14 by 14 by 3 image. The output will be what? 1 by 1 by 4 feature map, صح ولا? Okay, the output will be 1 by 1 by 4. So what does it contain? It will contain 4 values. So this is an image. It will tell about whether there is an object and the probability of the objects, let's say. Okay, now imagine that you have an image like this. It's a little bit bigger. Okay, so but my classifier, it will take only what? 14 by 14 by 3. It's possible that I take this part. Okay, 16 minus 2 pixels, it's what? It's 14. صح ولا? No, this is a bigger picture, let's say. Okay, so what is the size of the red square? So I can apply the same convolution here, صح ولا? It will result in what? 1 by 1 by 4. Okay. If I apply this red image here, red square image, into this convolution, what will be the output? Okay. Now, if I take this part of the image, the green one only, what is the size of the green image here? 14 by 14 by 3. So I can put it into the same classifier, صح ولا? Okay, imagine that now we are having sliding window. And the sliding window will take the same size of the image of the classifier. And now I will take this part of the image. It will also result into 1 by 1 by 4. And then I will take this part of the image. It's going to result into 1 by 1 by 4. Because all of them, they are 14 by 14 by 3. Okay? So at the end, what you will have? You will have one output for the red image. And one output for the green image. And one output for the orange image, and one output for the blue image. صح ولا? Okay, so all these outputs, they can be arranged into a 2 by 2 by 4. Okay, so this one will tell whether there is an object in the first red image, and this one will tell whether there is an object in the green image, and this one will tell whether there is an object in the orange image, and this one is going to tell whether there is an object in the blue image. Yes. Where? ايه هنا اول واحده اللي قبلها ولا ايش؟ Yes, 16 by 16 by 3. Yes. Let's say you have a stride of 2 لحجم على حسب الحجم هذا اللي هو 14 by 14 by 3. Okay, so this is my reference size now because I have a classifier with this size. Okay, and now I have a bigger image. So I want to detect all the object in this bigger image. Let's say I decided to make a stride of 2. Okay, so I will define a window with the same size of the input image of my classifier. زود عليها 2 by 2. Okay, so here we're going to have four regions. So the output will be also for the 4 regions. Okay, every region is going to tell here about whether there is an object detected in the corresponding square. هذا هو المبدأ الآن. هذا هو المبدأ اللي يعمل عليه الكونفولوشن. هذا يغير مفهوم. أنا الآن you don't need actually to make sliding window like this. What you will do, you will input all this image into the object detector. It will provide you an output like this. If you make a bigger image like this, it will make you a bigger output. So the output here will be dependent on the input image. Okay, it's not fixed like before. So it depends on the square or the square that you are going to use. Okay, let's say the grid here, the grid size that you are going to use for determining the output. واضحة الفكرة الآن الجميع؟ Yes. Classifier? Yes. الآن object detector. So the idea is the object detector takes the whole thing. أنا الآن وريت لكم التقسيم هذا مش نفهموا علاقته بالoutput to understand the relation between the input and the output. لكن the strength of YOLO and this object detector, it takes this whole image, okay, and it will provide an output like this, considering that it has a grid of this size. Okay, so now if you put another image, it will provide you a bigger output. So the output, it depends on the size of the grid that you will do. This is what we are going to call the anchors later on also. Okay, but now this is the idea of how to replace the sliding window by a convolution operation. So using this convolution, we are going to generate an output with a certain volume, okay, that depends on the input size as well. And then it will tell us in every part here whether there is an object or there is no object. Okay, so if you understand this, we can move forward, because everything else is going to depend on this one. So here, if we want to summarize what you're going to do, you're going to input an image. Okay, for example, you have an image like this, and every time you're going to this is not the concept of sliding window. This is the concept of the convolution is going to be applied to all these different regions to finally generate an output like this. Okay, until the end, it will detect that there is a car into a certain part of the image. Yes. No. Actually, we divide. It's not equal to the number of pixels is the width multiplied by the height. But we are in YOLO, we are going to divide the image into grid. Okay, we're going to divide the image into grid like this, and then we are going to apply every part of the grid to a convolution neural network to check whether there is an image found in the grid, in the selected grid cell or not. It's not 4 pixels. This is a volume that is 2 by 2 by 4. Okay, 2 by 2 by 4, it means 16 values. Yeah. So here, just take it simple. You know, we replace the concept of sliding window by a convolution. Okay, and the volume returned by the convolution, it will tell us about what are the object detected and what is the location of the object in the image. Yes. Yes, usually we take, we did this in the early slides. We take a window of the fixed size, and then it will, we will apply it for the whole image, and then we can take a bigger size. But So if you let me just move forward, you will see this window later on, we were going to call it anchor. Okay, and it will depend also on the object size that has to be detected in the image. So there is the concept of the grid. The grid are squares. We divide the image into grid like this. And every square, we're going to pass it into a convolutional neural network. But using this technique here, we don't need to pass every square of the image alone. So we will pass the whole image into the convolutional neural network, and finally, it will return as a volume like this. Okay, so in the object classification and localization, if I come back to the previous slides, okay, we're going to only locate one object. Okay, one object, so I think this is clear. It has the probability of whether there is an object or not, the bounding boxes, and also the probability of every object that appears in the image. Okay, so for the object detection, okay, the native way is actually to make sliding window like this. But as I told you, this technique is not very efficient in terms of computation. Okay, because we need to choose several window sizes, and we need also to run for, it will run for a long time. And the accuracy is not also guaranteed. These are the problems of the sliding window. So what was the solution? We changed the sliding window by a convolution. So first of all, we have introduced the one-by-one convolution that replaces the fully connected layer. And then we have applied this, okay, to calculate the output of one image. So this image now is going to provide an output 2 by 2 by 4. And this output is going to provide the information of every part of the image here, okay, whether there is an object or there is no an object. And of course, if you change the image size, you will have a different output volume. Okay, so the objective of this technique is to replace the sliding window approach, which is actually not very efficient. This is one of the techniques that were proposed for state-of-the-art object detection algorithm in order to speed up the detection. There are other techniques, like for example RCNN and faster RCNN. I'm going to explain in the next lecture. But YOLO, the design of YOLO, make it the fastest object detector algorithm for so many years now, the previous 3 to 4 years. Okay? Yes? No. These are just some simple examples of input images. Okay? These are just some assumptions, you know. These are the filters of the convolutions. Oh. Wait. Yeah. No, if you apply a filter 5 by 5 over 28 by 28, you will find this number. Yes, if you remember the convolutional neural network lecture, we talked about how to compute the dimension of the feature map if we apply a certain filter with size f, and we have an input image with size n. So it's the same formula that we apply. Okay. But now the most important thing is that for every input image, you will have an output volume, okay, such that is going to tell where the object is located and its bounding boxes. That's the whole thing. واضح? And now, doing that, we will have a problem that is called the intersection over union. So imagine that you have a cut like this, okay, and you made a labeling of the cut. So this is, let's say, the ground truth bounding box. This is the bounding box that is perfect, and that you made it during the labeling, and this is actually what should be predicted by your object detector. But later on, when you applied the object detection algorithm, you find that this was the detection of the cut in the blue area like this. Okay, so we can see that there is some deviation. It's difficult, or probably is impossible, to have exactly the same ground truth label box. Okay, there will be some differences. But now, should we accept the bounding box in blue that it is for a cut or not? Okay, now this is the question. And for this, we're going to calculate what we call the intersection over the union. What does it mean? First of all, we are going to calculate the union. That is the blue shaded area. So this is the union of the two squares, the ground truth square and the predicted square. And then we're going to calculate the intersection. So this is the intersection. And the rule here is that the intersection over union is called the IOU, has to be greater than a certain threshold. So in the literature, most of the papers, and they propose to use 0.5 as a threshold. What does it mean? If the intersection, this yellow area divided by the blue area is greater than 50%, then in this case I will consider that the detection is valid and will be taken into account. Otherwise, I will not consider it as a correct detection. واضحة الفكرة؟ Yes. So, you don't choose the union. Until الآن, this is the correct bounding box, and your classifier has provided this bounding box. Okay? So you want to know now, should I accept this as a correct detection? So you have the information of the ground truth, and you have the information of the predicted box. So you will calculate the surface of both, that is the union, and you will calculate the intersection, the intersected surface, and then you divide the intersection by the union. If you find that there is an overlap more than 50%, then it's okay. I can consider this as a correct detection of the object. If it is below than 50%, I will consider that it is not a good fit. So 50%, this is a value that is a convention from the community. Some people, they use 60%, some people, they use 70%. You can also be more strict, 20%, sorry, 80%. So it depends, but usually it's either 50% or more. So it's not likely to put it 40%, because if it is 40% only, it's like it's not the correct object for the intersection. You might want to look for another bounding box other than this one. Okay, so this is the concept of intersection over the union that we have to calculate. Okay, this is small Python code that tells you if you have two boxes characterized by x1, y1, w1, h1, and the second box x2, y2, w2, and h2, how to calculate the intersection, how to calculate the union, okay, using the following formula. You can test it at home if you want. Okay, so this is the summary. The intersection of a union, it's known as the IOU, is a function that quantifies how correctly positioned a predicted bounding box or the actual bounding box. Okay, so it will compare the predicted over the ground truth, over the actual one. So for example, if this is the ground truth in white, and you find the predicted as the blue one. So here you have an IOU only 0.1. It's very low. So you won't say that this blue area is a teddy bear. Okay, now if we look at the second case, this is the ground truth, but you find that this part is actually 0.5, the IOU with the blue surface. So in this case, you can say, yeah, here it's likely that it is a teddy bear. And if it is really a big overlap, like here, there is 90% of overlap, so here you have more confidence that the bounding box is correct. Okay, so the intersection over union, it gives you an indication about the correctness of the bounding box with respect to the ground truth. That's why the lab link is very important, the correctness of the lab link, because later on you are going to compare the predicted labels or the predicted bounding boxes to the ground truth bounding boxes. Is it clear? Yeah. Yeah, so here we say it's wrong, you know, it's something lower than 0.5 is considered as wrong. Okay, because look, it only takes a very small part, only 1/10 of the area is overlapping. Okay, so I won't consider that this bounding box is providing a correct detection. واضح? Because even with the human eye, if it just gives you this part that is in blue, will you tell that it is a teddy bear? You know, you have a book, you have a teddy bear, so there is nothing that is really clear. So here, it's clearer than the previous case. And here it's even clearer, okay? Because the predicted bounding box is the one that is going to give you the confidence about the detection. Yeah. Sorry, provide the solution of what? Yes, yes. Yeah. Yeah, because now this comparison is possible when you have a test data set. Because in the test data set, you have the correct bounding boxes. Okay? But later, so we do this during the testing phase. The testing phase, the comparison between, or even during the training. Okay? The comparison between the ground truth and the predicted. So, during the training is going to learn how to predict the correct bounding boxes. And during the testing, you can check whether the bounding box has a good overlap with the ground truth or not. Okay, and based on this, you will decide whether the detection is valid or not valid based on the overlap. Usually, it has to be more than 50%. So, and of course, if you increase the IOU threshold, you will decrease the probability of detection. Okay, so for example, now, if I put an IOU equal to 0.5, now if I give this one to my predictor, it's going to say, this is a teddy bear, yes. So it's going to add you 1 to the prediction. But if I put 0.9 as a threshold and I provide this value, so it will not be considered that this one as a teddy bear. واضحة الفكرة؟ Okay. So now we have another problem, that is when you run the object detection algorithm, it's possible and it's very likely that you are going to detect several bounding boxes for the same object, like you can see here in this picture. Okay, so the problem is that the object detection algorithm may find multiple detection of the same object. Rather than detecting an object just once, it might detect it multiple times. And this is a big problem. Okay, so which one to choose? Because I'm going to run the detection algorithm for different window sizes, okay, and every time it's going to detect an object or a bounding box for the image. So the solution to this is called the non-max suppression. So simply it means we are going to calculate different bounding boxes, and we will eliminate the redundant bounding boxes that have low confidence. Okay, and now we will see how to determine the confidence level such that we are going to remove the low confidence ones. This is what we call the non-max suppression. So ideally, every car instance should have only one midpoint, that is the center of the car. But the problem now, if you run your algorithm, so maybe this square here is going to tell you there is a car here. This square is going to give you another bounding box centered at this cell, or this cell, or this cell. So you have a lot of cases that probably is going at the end to return you something like this. Okay, so for this car you have 2 bounding boxes, and for this car you have 3 bounding boxes. Now which one to keep? So there is an algorithm that we have to run that is called the non-max suppression to clean up all this detection and only keep one detection by car object. So first of all, we need to look at the IOUs, and we need to keep only the IOU with a certain threshold. Okay, let's say we put an IOU 0.5, and then it will return 2 bounding boxes for this car and 3 bounding boxes, and you can see that all the IOUs will be greater than 0.5. And then we are going to look at the probability of the detection. So this bounding box says that it's a car with 90%, and this bounding box says that this is a car with 60% accuracy. And this one, it says that this is a car with 70% of accuracy. So what we will keep, we'll keep the maximum probability of detection. So 0.6 and 0.7 are going to be removed. So same thing here. If we compare 0.7 and 0.8, we will keep only the maximum probability of detection. Okay, so finally you will end up with only one bounding box per prediction. Yes? Yeah. It depends. It depends on several parameters. The size of the it depends on the size of the grid that you will use. Okay. It depends how close these 2 objects are together. It depends on several parameters. Now I am presenting the elements of the algorithm, but later on there are some other elements that are used in the real detection algorithm that I will provide. I will present just in a moment, like the anchor, for example. Okay. So now this is the concept of the non-max suppression. Simply, we will keep only the bounding boxes that has the highest confidence or the maximum confidence level. Okay, so the algorithm here, when you have an output prediction like this, so probability of detection of the object and the bounding boxes. So first of all, we are going to discard all the boxes smaller than with IOU. We are going to discard all the boxes with a probability of presence of the object smaller than 60%. And then, while there are remaining boxes, we will pick the box with the largest PC output, probability of prediction, this one. And then discard any remaining box with an IOU greater than 0.5. Okay, so this is a slide summary about the non-max suppression algorithm. Now, another important issue in object detection is that not all the objects they have the same dimensions. Okay, now if you use square anchors, maybe you will not be able to detect all the objects because, for example, you might have objects that are tall like this, like a person, and you can have an object that can have some other dimensions. Okay, so in order to solve this problem, the YOLO paper they have proposed to use what we call anchor boxes. So what are anchor boxes? Is a technique used to predict the overlapping bounding boxes. And in practice, the network is allowed to predict more than one box simultaneously, where each box prediction is constrained to have a given set of geometrical properties. So the idea of bounding box is the following. We're going to have to determine some possible shapes of objects. For example, if I'm going to detect cars and humans, so I will say I will have an anchor box like this that is dedicated for humans, and I will have an anchor box like this that will be dedicated for cars. Okay? So in this case, your output, you will have an output per anchor. Okay, so if you use two anchors, in this case, you will have probability of presence of an object for anchor 1, then the bounding box of anchor 1, and then the probability of each class for the anchor 1. And same thing will be also for anchor 2. So each anchor will have its own bounding box properties and its own probabilities. Because now, for example, if you put anchor 1 for the car, maybe it will not detect the car, but if you put anchor 2, it will detect the car. Okay, so same thing for if you want to detect a person with anchor 2, because the size of anchor 2 was designed to fit the shape of a car, and the size of box 1, the anchor box 1 was designed to fit the shape of the person. So actually the selection of anchors is very important for the performance of the algorithm, and it tries to predict the shape of the object to be detected. Okay, so now for example, if you have multiple anchors, in this case, you will have to encode your output, okay, such that you have an output for every anchor, like you have seen in this example here. Okay, so now we come to the YOLO algorithm, which actually put all together these different operations and approaches. Okay, and now for example in YOLO, if you have an image like this, okay, you have an input size. So you will first of all divide your input image into a grid. Let's say 3 by 3 by 2, 3 by 3, a grid 3 by 3. And here you will define two anchors. Let's say an anchor for pedestrian and an anchor for cars. Okay, so this is the number of anchors. And here the output size per anchor. So imagine that you have two anchors, one for pedestrians and one for cars. So for every anchor you are going to have 8 outputs. What are these 8 outputs? It's the same outputs that we did for object localization, the probability of the presence of an object in the image, and the bounding box information, and also here the 3 classes. This is if we have 3 classes. So in general, it's 5 plus the number of classes. Here we assume that we have 3 classes. The class 1 is for pedestrian, class 2 for car, and class 3 for motorcycle. Yes. Sorry? You can have as many anchors as you want. Okay, so you can define your anchors either manually, or in YOLO you can actually define or optimize the anchor size with respect to your data set. So usually the good practice is that you optimize. There is an algorithm that optimizes the anchor sizes with respect to the object to be detected in the data set. But you can set your anchors manually. Okay, but you don't have any guarantee that the performance will be optimal. Okay, so usually we have an input size of 3 by 3 by 2 by 8, and the output will be of size 3 by 3, because here we have a grid of 3 by 3 multiplied by the number of anchors multiplied by the output size per anchor. Now, for example, if we take the first element in the grid like this, so this one, it will correspond to a vector that is 0 because there is no object, and for the first anchor, 0 and then some ignored values, and same thing for the second anchor, there is no object, so 0 and some ignored values. Now, if we consider this cell in green, okay, it's this one. So here, if we apply the first anchor for pedestrian, it will be 0, and if we apply the anchor for the car, it will give you 1 here as the probability, then the coordinate of the bounding box, and then it will give you a 1 for the probability that it is a car. Okay, so you can see the output of YOLO, how it is designed. You have an output per anchor. So now if we apply the anchor of the pedestrian, you will have 0 here for this particular part of the grid. And if you use the anchor of the car, in this case you will have the following input. And of course you can have different anchors, because the car, you can have it from the back side, from the front side, from the side level. So you can have several anchors even for the same object. And in this case, your output will be multiplied by the number of anchors that you will have. واضحة الفكرة? Okay, so YOLO algorithm, it will apply the convolutions in order to find the output vector, and it will use the non-max suppression to only keep one bounding box of the image. So this is here a summary. Okay, let's assume that you have an image like this. So what you will do, you will first divide your image into a grid. Okay, so here we have a grid 4 by 4. Grid 1, grid 2, grid 3, grid 4, until grid 16, because you have 4 by 4. So our output will be, this is the size of the image, multiplied by 3, multiplied by 16. Okay, so now all the grids here are going to return 0. But let's look at the grid 7. Okay, grid 7 here. So this is the origin of grid 7, 1, 1, and 0, 0, and this is 1, 1. So grid 7 is going to provide an output vector like this. Probability of that there is an object will be 1, okay, because there is an object detected car inside this grid. And then it will give you the bounding box coordinate 0.8, 0.9. Look, this is the point here. It's located at 0.8 in the x-axis and 0.9 in the y-axis. And then you have the height and the length, 1.5 and 1.2. Look, the bounding box is a bit greater than the size of the grid here, because you have used an anchor, okay, corresponding to this size. And then the probability that this is a car is equal to 1. And then probability that it is a light 0, probability of pedestrian is 0. And of course, for all the other cells, it's going to be equal to 0. So the car is detected at the grid number 7. Yes, yes. It will search with respect to the size of the bounding boxes. until الآن لما تسوي labeled data set, you will define a bounding box for every object, صح ولا لا? So based on the bounding box size, it will try to find the best dimension of the anchors. Okay. مثلا اغلب البوندينج بوكسز مثلا let's say 100 pixel by 80 pixel. Okay, so it will make an anchor close to these dimensions. واضح؟ Yes. No, before the training. The anchor is something that you specify before the training. The anchor you can specify manually. أنت الآن تقول مثلا I want the anchor to be of this size. Okay, 100 pixel by 50 pixel. And another anchor like 20 pixel by 30 pixel. You can do this manually. Or you can say there are some algorithms that will take your data set as input, and it will try to determine what are the best configuration of anchors automatically before starting the learning. فهمتوا ولا؟ Because the anchor are hyperparameters that you have to set in advance, and the performance of the algorithm will depend a lot on the anchor size. Okay. The anchor is like the bounding box, is the expected shape of the bounding box. Okay, and the bounding box is the one that you either put in the data set when you label the data set, or that the algorithm is going to predict at the end. Yes, and in order to guide the prediction algorithm, you will tell him what is the likely expected dimensions of the predicted bounding boxes. مش ما تخليش يضيع. فهمتوا ولا لا؟ مثلا إذا كان كل الأوبجكت بتاعك as a car like this, and you provide the bounding box like this, for example. Okay, it will not be very effective, a bounding box like the blue line here. Okay, because it will be different from the shape of your object to detect. Okay, that's why we are going to provide several bounding boxes depending on the object dimensions, the object that we have to detect. واضح؟ Yeah, it's not the problem, because here you are going to learn. So the algorithm is going to learn how to determine the center point and the bounding box. Yeah, it searches for the center. This is the learning, how it's going to do. This is the concept that we have provided in classification plus localization. It will be applied grid by grid, okay? And finally, it will draw the bounding box. So you will have actually an assignment, programming assignment, that you will go through all these details, inshallah. Okay, just to finalize, here a summary of the YOLO algorithm. So first of all, you divide your image into a grid that is G by G, like this. Okay, and for each grid cell, you run a convolutional neural network that predict the output Y, هذا output Y. That is the probability of the object, the probability that there is an object, the bounding box, and which class. So you repeat this K times. What is K? Is the number of anchors. Okay, if you have 10 anchors, you will have 10 possible outputs, one output per anchor for every grid. Okay. So then you run this is going to give you for the same image several bounding boxes, as you can see here. For example, 3 bounding boxes for the teddy bear and 2 bounding boxes for the book. Then you will apply the non-max suppression algorithm to remove any potential duplicate overlapping bounding boxes, and finally you will get the teddy bear only 1 bounding box and the book only 1 bounding box. This is in summary the YOLO algorithm. So you can have also more details in the YOLO paper. So you can type YOLO paper on Google, but I know that it is one of the difficult paper to read, but still it provides more details about the algorithm. But in summary, this is the idea is you need to divide into grid, then you will define an output for every anchor, and every output is going to provide information about whether the object is present, the bounding box of the object, and also the class of the object. Yes? You don't assign anything. First of all, you have to label your data set. Okay, you have to do data set labeling. Okay, and labeling, it means you are going to provide yourself manually the bounding boxes of the object. Then what you provide in the training algorithm, okay, you will provide an image, you will provide the information about the bounding box and the information about the class. Same information as here. So this is what the training algorithm is going to learn. Okay, and then the algorithm is going to learn how to optimize, okay, the bounding box for every object that will be detected in the image. Yeah. Any other question? Okay, thank you. So we come to the end of the lecture of today, and I will send you the assignment. We will come back again in the programming assignment to understand more the details about the algorithm from implementation perspective. And we will do also some other kind of object detection algorithm, because this is one of the hottest area now. Even if you go to the industry later on for companies to work on deep learning, okay, the most important projects are about object detection. So I will provide you the different variations of object detection state-of-the-art algorithm. We will talk about efficient DET, we will talk about faster RCNN, and we will also look at the implementations of these algorithms. Okay, thank you very much, and we come to the end of the lecture.